We are a consortium of Earth observation specialists working for the European Space Agency.
The framework in which we operate is twofold. The first guiding principle is the United Nations Sustainable Development Goal 11. Make cities and human settlements inclusive, safe, resilient and sustainable. The second framework is the Project Implementation Strategy in international financing institutions like the World Bank and other development banks.
Our aim is to extend and improve the use of satellite data for the monitoring of indicators in order to reach Sustainable Development Goal number 11. We also want to facilitate international development work in a globally consistent manner by using Earth observation data and methods.
We have covered 32 cities around the globe with a total of more than 510 products and 11,000 square kilometers mapped. Our basic products comprise status and evolution of urban extent, as well as land use and land cover and its change over time. More specifically, targeted maps include slum maps, maps of open and green spaces, building footprints and heights, infrastructure, as well as hazard and risk maps. Based on these maps, we generate spatial analytics and the before-mentioned indicators for SDG 11.
These tools are very much relevant because they provide evidence.
In general, the preparations of bank operations take several years, but in these cases, it only took around 6 to 8 months for the preparation. Thanks to the whole analytics, maps, and data evidences. The best part is that it was helpful to communicate with various stakeholders on the ground.
We have today 2 speakers. First, I would like to introduce Fang from NEO in the Netherlands. Fang will talk about flood history, hazards and risk products, which have been produced within the frame of this product, and she will also talk about the use case in Dhaka. The second speaker today will be myself, so I will give you first a bit of the background. So what are the Sustainable Development Goals with regard to disaster management city plans, and also the Sendai framework for disaster risk reduction. Then, as I said before, point 2 and 3 will be covered by Fang. And then I will give you some details on the terrain and infrastructure motion product, which we have derived within the product, and then show you the use case of Semarang. Finally, we have a short conclusion and question and answer session. Okay, so as I said, we'll start now with the background. You probably all are aware of the UNDP Sustainable Development Goals. And the UNDP Sustainable Development Goal number 11, Sustainable Cities and Communities. Within this goal, we have the target number 5, which is that by 2030, the aim is to significantly reduce the numbers of deaths, people affected, and also other damages to any economic damages caused by disasters, including water-related disasters. So the aim is to reduce these numbers. And there is a special focus on protecting the poor and people living in vulnerable situations. So considering this target, there are several indicators which we can monitor over time to see whether we are on the right track to achieving this target. One of these indicators would be like an estimation of people living in high-risk areas, for example. Or another thing is the estimation of people living in slums or inadequate housing within high-risk areas. And with that, I also want to refer back to one of our previous webinars, the webinar 3.2 about slum upgrade and access to basic services, which is also connected to this indicator. With regards to the Sendai framework for disaster risk reduction, there are similar indicators to be monitored. For example, the economic loss due to houses damaged or destroyed, agricultural loss, crops, livestock, other losses to industrial facilities which were damaged or destroyed, or critical infrastructure damaged or destroyed due to hazardous events. So all of these indicators can be monitored to some extent using Earth observation. So for this, of course, not everything can be mapped with Earth observation or remote sensing methods, but there are some really significant parameters which can be done. So the first, and this will be today the main focus, will be the mapping of risk areas for floods, for terrain motion. There are also landslides. So all of these rock falls, all of these risk areas, they can be modeled or mapped with the use of the help of remote sensing data. Then also, of course, land use information. So if we are talking about residential areas affected by floods. We need to know where is the residential area. Industrial complexes, for example, the same. So we can map the industrial areas and then estimate over time or track over time whether this is increased or decreased. So whether we are going in the right direction to achieve our target or not. Transport infrastructure is the same, especially critical infrastructure like railway systems. And then there is this group of building footprints, building heights. So you can imagine also that it is important to know the size of the buildings that are affected. If you have a big skyscraper, it will be much more damage if this one gets cracks, let's say, due to some disaster, or if it's just a small hut or something. And this is also connected to the population distribution. So what we can do is that we use census data and distribute by the help of AO data and information based on building heights, building footprints, information on the land use, where these people are approximately living. So that's a population distribution estimation. And all of this can help to map and monitor these indicators I've mentioned previously. Okay, so this was a bit of the background, and now I would like to give the floor to Fang for talking about the flood risk products, and then I will come back to you with the terrain motion. So Fang, the floor is yours.
Yes, thank you, Manuela, for the introduction. So can you see my screen?
Not yet.
Not yet. Okay. How about because now I already have you. So should I share my screen, or you can do it from your side?
No, you have to agree to share your screen.
Okay. Let me see.
There should be a window popping up somewhere.
Yeah. Show screen.
Yes.
Yes. Okay. Great. So hello everyone. Welcome to the webinar. My name is Fang Fang, and I'm a geoinformation specialist from NEO. Today in this presentation, I would be talking about flood risk products and share with you some use case and feedback. Hopefully that this could give you an overview of the product and help you understand better about its usability and the potentials. For those of you who have been attending previous webinar, you probably know that EU4SD project, Urban Development, is one of the series projects initiated and funded by ESA. So the purpose is to demonstrate the benefits of EU-based geoinformation products and services for support urban planning tasks and the local community development. So the flood risk product is one of the products we provided in this project. And today I'm going to introduce you briefly about the flooding events in the countries where this project is operating. And then I will talk about briefly about the role of EU data, how can it be used for producing flood risk maps, and the flood risk product itself, of course. And also would shortly talk about methodology and the workflow behind it. And in the end, I'm going to show you the case we did in Dhaka. So, so this map The orange stars that you see here is the cities where we have producing flood risk products in this project. And all of these cities, they usually have flood events, and they share some common points. The first one is that all of the cities, they are frequently flooded due to seasonal floods or flash floods. For instance, the cities in Cambodia, they suffer from the flooding caused by monsoon season. And usually when there are big or significant flood events happen, and during these events, there are usually life loss or large economic loss. Later, you can see an example from Cambodia. And though all of these cities, they are exposed to frequent flood hazard. However, there's a lack of effective long-term plan to mitigate the risk. And so this is an example of the Cambodia. So in the table here, there are 4 cities, and we have done flood risk products for. And these cities, they are all located around the Tonle Sap region in Cambodia. So during from 2007 and 2013, between the 6 years interval, you can say that all of the cities have been flooded 4 times, and some of them even been flooded 5 times. So that means every 1.5 years, there's a flood. And how about the scope? So the figure here tells it is a flood extent map from one event. And you can see here for the first city, 90%, almost 90% of the city was flooded. And the inner circle is the core urban area, and the out circle is the pre-urban boundaries. So for the Cambodian, for example, this core urban was about 60% flooded during one significant event. So it was a really bad situation. And the estimation from the Mekong River Commission says that each event, the annual flood usually costs $60 to $70 million damage. And usually it takes 2 months or even longer time for the floods to go away. So the conclusion is that all the cities are very vulnerable to flood hazard. To minimize the damage, both short-term and long-term city planning strategy is needed. And to do that, an overview on the flooding history, information on the event, and quantitative data analysis is needed. So here is where the Earth observation data jumps in. And some of you may have attended the first webinar before and learned about the term remote sensing, which is a technology of acquiring data about the Earth's surface. So you can see from the figures here that there are sensors onboarded the satellites, both in active and passive mode. They are continuous sense the Earth and acquire information and sending back this information to the ground. So with this scale and this different spatial resolution and the temporal resolution, we could trace back the historical flooding events to understand its scope and mechanism and the impact it brought to local cities. And also, whenever there's urgent flooding case happens, the EO data can be acquired to generate information for the purpose of support decision making and to guide the action, the response action. So with complete and comprehensive information obtained from EO data, the decision makers could adapt the plans to mitigate the risk. And most importantly, in the long run, to design the city in a way that it's more resilient to such natural hazards, both in terms of humanity and economic aspects. So for instance, they can do better plan to improve the water drainage system and protect the wetlands, and also implement some early warning system. And this would be more effective measures in the long run. And so back to the flood risk products. Actually, it includes 3 products: flood extent, flood hazard, and flood risk. So flood extent, by its name, it tells you how big is the flood. So the extent of the flood at a specific time can be derived from a satellite imagery. So if we derive the extent of the floods at a different time through the flooding event, then we could know how the flood spread in the city and how it degrades. Second, flood hazard. It tells you how often is this area flooded. So it doesn't tell you the probability, but it tells you the facts, how often it has been flooded during the past within a specific time window. So you can see in this picture that the blue is the river and the other color are the flooded area. And the darker the color is, that means this area are more flooded. So like this orange color here indicates that it has been flooded 4 times in a 10 times interval. And last, the flood risk. This is the most interesting product, as it shows you how risk it is. Within a city, different area have a different risk level, and this is because different land use. So for the place where there are more people or more expensive infrastructures, it would have a higher risk when it's exposed to flood hazard. So I'm going to talk briefly about the methodology behind the flood risk product. So the flood risk in the EOFSD project is assessed in 2 perspectives. First perspective is flood hazard level, and it's similar to flood hazard product. It tells you how often this area is flooded. So it takes the flood hazard product into as an input, and it categorizes further into 3 classes from 1 to 3. 1 stands for a low hazard level, and the 3 stands for high hazard level. And the other perspective is the damage level. So each land use land cover is assessed on 4 aspects. The table here shows that the 4 aspects, it's about economy, about social damage, and physical damage, and the flood duration. And on the right column here, then you can say that what are the concerns and things covered by each aspect. So another table, this is a land use land cover damage table. And you can see here on the first column, it's a different land use land cover in a core city area. So for each land use land type, the damage level is assessed on these 4 aspects from a scale of 0 to 2. 0 stands for no damage, and 2 stands for a very big damage. So these scores further summed up to a total score here between 0 and 8. And then they are further categorized into 4 different damage levels, where A stands for low damage level, and D stands for highest damage level. So we take into account how frequently the flood happens on the right side here. And then we also take into account the damage level using the land use and cover information. So then when we combine these 2 perspectives, we come up to this final risk matrix, where the risk code is represented by 1 digits about how frequently, how often, and a letter which indicates the damage level. So from the left upper part, it indicates a lower risk level, And when we go to the right and lower corner, then the risk level increase to the to 3D, which is the most the highest risk level. And the table here shows you the same concepts of this flat risk. So that's briefly about the methodology. And when we do a flat risk product for a city, we always start with flat inventory about the historical events and how significant. And then from there, we start data collection. We not only collect the Earth observation data, but also, by the way, we also collect elevation model, land use cover, and administrative boundary, etc. Other data that might be helpful in the analysis. And from there, we derive the flood extent for each flooding event. And by combining all the flood events, we derive flood hazard. Then together with land use, land cover information, we derive the flood risk product. So here is one case that we did in Dhaka. Dhaka is the capital city of Bangladesh, and it's one of the biggest cities in Southeast Asia with 20 million people living there, and it's now fast growing and developing. However, urban floods is one of the main hazards it's facing, and the city has become more vulnerable to this intense urban flooding because sometimes it has heavy and unpredicted rainfall. And you can see here that the table here shows some recorded significant events between 2004 and 2016. And the pictures here shows the flood extent of that of 2004 and 2014. So the darker blue is the original water body, and the lighter blue is the flooded area. And flood hazard. So this map, this map here shows the flood hazard. So you can, and the color indicate how many events happened during the 10 years interval. And you can say that most of the area have around 2 or 3 events. Together with land use, land cover information, we derive this flood risk map. So most of the area has a medium risk, but if we zoom in further, here we see some orange color indicating a high risk level. And this is because along this region there are 2 train stations, and it's also a very highly populated area. So that's why the risk is higher. And there's one, here are some statistics. So for per urban area, around 56% of the area are exposed to risk, and with 40% are medium risk and 17% are low risk. And in core urban, you can say that it's only 43% area are exposed to risk, while 27 are medium risk and 16 are low risk. This is because the core urban area is situated or located in a higher elevated place. So that's why the percentage is smaller than the pre-urban area. And in terms of agriculture, so I'm not surprised to say that it's 72% and 85% in pre-urban and core urban area, because the map that you and the figures that you just saw, that most of the flooded area are in agriculture place. However, this is a problem because agriculture is also one important part for the city Dhaka, and as there are more people migrated to the cities, and it causes pressure on the agriculture as well. And there's one thing I want to mention is that during the middle August 2017, so a big flood event occurred, and we were contacted by our project partner to produce the flooding map for local users. for emergency response. So we immediately took action to search and process available EO data, and were able to produce the flood extent map within 1 day or so, and delivered to ESA and the clients. This was highly appreciated, as this quick response could allow local emergency team have a clear overview of how large the scope is and where are the areas flooded. And together with other asset information, they could make more evidence-based decision on action plans, and such as where to send the rescue team in a swift manner. And we also got some feedback from our client. So Xunji Li, she's from the Urbanscapes team of World Bank, and she has gave us some feedback. And she has also did a presentation in last webinar. And if you're interested, you can go to our website and check the presentation where she showed how our data has helped them to design projects for local community. She has worked closely with our consortium partner, GSAT, to understand and make use of the EO4SD products and services for local development projects from the World Bank. So at the generic level, the EO4SD urban products, including the flood risk products, offer a systematic and contextualized understanding of urban assets and public spaces, which allows for comparative analysis. And for some of the cities that the project is operating, usually it's developing, so it lack of data, and this disadvantage could be covered by using EO data-based products. And to be more specific, she listed 3 advantages. So with the product, they're able to reduce costs and the time for understand the city. And originally, it probably needs to be done by manually and field inspection, which would take much longer time. But now with EO data, it become more possible with larger scale and within a short time. And second is to improve the project design with evidence-based approach. And third is with what is statistics and figures, they are more convincing and they would have better communication with local partners. So to give you an example, to reduce the cost and time for the preparation. So usually the World Bank, they have a number of local community upgrading projects running, and that is one of the city. So the projects are aimed to enhance the public space and improve urban services in selected neighborhoods. Usually this kind of project, it would take several years for the bank to do preparation. However, with the help of the EO4SD products, it only took them 6 to 8 months. And this is a very interesting project. And if you want to know more about the project and how the products are used in the design of the improvement project, you can go to the link here. And in this blog, Xunji Li has provided a lot of details, and with figures, it's nice to see. And another example, that evidence-based approach. So when they design a project and they want to select neighborhood, the yield-based product allows them to perform this kind of spatial analysis. For instance, this is how accessible the local community is to infrastructure and to the public transport. And also this kind of analysis allow them to be better informed about local needs. And this is very important for them to design their projects. So yes, that's what I want to share with you today. And thank you for your attention and interest. If you have any questions, please post them at the end of the session, and I would be really glad to answer them. Thank you.
Thank you, Fang. Yeah, you can already, if you want, you can already now post your questions. Okay, and now I want to talk a bit about terrain and infrastructure motion. So what is terrain motion? Terrain motion is the upheaval or the sinking of land, which can be due to various causes. Today, upheaval is not so common, but sinking, or also said subsidence, is often caused by several reasons. One is that there is an increased pressure on the surface due to concentrated building activities. Of course, not only, but in combination with a geological disposition in the underground, together with groundwater extraction or mining activities. And then this subsidence can have severe effects. It can cause cracks and damages to buildings and infrastructure. It can even cause collapsing of buildings. And as you've seen before, the floods, if this location is close to the sea, of course, there's more frequent flooding, also in consideration when there is a sea level rise. So if the sea level becomes higher and the land sinks, it's even more drastic, the result. Now I want to show you the same on some Google Earth pictures. So you can see this area here, it's close to so there's the sea, there's the land, and there is some agricultural areas in the coastline. In 2003, you can still see the individual fields very clearly. In 2007, already part of it is underwater or completely underwater. And then in 2016, all this area is basically gone. So this is really a strong situation where you have a sinking land at the coastline and the sea potentially in combination with the sea level rise. So now, how can we monitor this area? You can already imagine that it's important to know where and how fast this land sinking is going on. And you can also imagine that it's not meters that is sinking in a year, so it's centimeters. So how can we measure that from space? There is a very clever system behind it, and I'm not going to explain it in full detail, but just give you an overview. We can use SAR data, so it's radar data, an active system. If you want to know more about active remote sensing systems, I would like to refer back to webinar 2.1 in the recording where it is very well explained. But just to give you an insight, so that an active sensor submits a pulse to the Earth and then measures the echo. From that, the distance can be measured. And if this is done repeatedly, you have several distances, basically. In the SAR data, this is measured in terms of interferogram when you have two measurements, like here the satellite flies over and it measures the ground, so to say, and then you get these wavelengths. This is the wavelengths of the sensor, so the signal which is transmitted and received. And based on this shift, this difference between two times, for example, can be measured. And as you see here, the wavelength is in centimeters. So that means this delta here can be transformed into height difference. So we can really measure this kind of differences in the centimeter frame. You can also imagine that this will only work on, let's say, areas which look the same. So we need to find an area on the ground which looks the same on all the, or on two or more points in time when the satellite passes over. So for example, for agricultural areas where the grass is growing, or crops are growing, or for a forest, the wind is moving and is growing. So there you have no coherence, so that the area is changing too much. So you cannot estimate this kind of terrain motion. But you can do it very well on built-up areas, because the houses, they look quite the same, so to say. So you can see here that for these points here on the build-up areas, we could derive these subsidence rates. And then these points can be used to interpolate, so that we get a full areal information, and also for these areas where we have no points. And this can be used together with infrastructure information. As I've said before, we have from Earth observation data, you can derive the road network, railroad network, etc. So you can calculate the road kilometers affected by the different subsidence rates. And you can see the rates up here, that the green areas are 4 to 6 centimeters per year, and then it goes up even to 12 centimeters a year in some small parts in Semarang. And the same as you do with you could do with the road network, you can also do with the land use. So if you want to know how many square kilometers of residential areas are affected by a certain subsidence degree, you can combine this. Okay, so much to the background, and the examples I've already shown are also all from the city of Semarang in Indonesia. And this use case in Semarang is based on the CPL Technical Assistance Program, the City Planning Labs from World Bank. And the aim of CPL is to assist member cities by turning data into information, to institutionalize data governments, to enable evidence-driven urban planning, so to improve urban planning. Specifically, it should enable the municipal governments to produce, share, and utilize spatial data for sustainable planning. So that's the main aim of this whole city planning labs, and we provided them with some data. For Indonesia, the city planning labs is working in close cooperation with 3 partner cities. This is Semarang, Balikpapan, and Denpasar. We provided data only for Semarang and Denpasar. And for these cities, CPL has developed this municipal spatial data infrastructure implementation roadmap. So in order to close the human resource gap for geospatial capabilities. So they also do a lot of training and capacity building to do that. You can find the source of these statements below. Now this is a result. So what we did in Semarang was not only a terrain motion, but also the connected flood risk. You can imagine, I've shown before, that when we are talking about a coast city, that sinking land at the coast is, of course, then means also more flooding, more frequent or more severe flooding. And this is an example where we included not only, as Fang has shown before, not only the past flood extents and the land use to produce the risk, but also the subsidence map. So we included the subsidence of the last years to forecast the risk, because of course if you measure higher rates of subsidence, then also the risk will also be higher, but the hazard as well. And of course, as I already mentioned before, you can derive all kinds of statistics, both for the flood risk and also for the terrain motion products. So this is an example. If you want to know how much area or percent of the industrial, commercial, and public areas is affected by the different subsidence categories, you can generate it for the whole city, for several cities, etc. So you get really nice quantitative information on that topic. Here's that example for residential areas which are affected by different subsidence classes. So what? So we delivered these products, and what did the user say to this? Here it's mentioned that through this partnership with the ESA and with us as the consortium, CPL initiated the mapping of geospatial data for Semarang. Denpasar using satellite imagery. They accessed state-of-the-art radar data through us in Semarang to trace this land subsidence. And the special agency of Semarang, Distaro, immediately used this data. This is very nice that they use this data to inform decisions being made on a special plan. And through the use of these Earth observation tools of ESA on urban growth patterns, Semarang and Denpasar also utilize remote sensing technologies to develop core data sets, which are very relevant to the cities, which effectively helps them to develop fundamental data sets, FDS, I think it's fundamental data sets they so far did not have. So this is very nice. And then another part of the feedback, so this previous one was in the data report, and this one is from the people report. So here they say that using this newly developed data, CPL worked closely with the city government to increase awareness about the benefits of the use of radar data to map these terrain motion occurrences. And in coordination with the municipal planning, this Papeda and Semarang Spatial Planning Department, Distaro, has already used the land subsidence data that was produced for the preparation of the spatial planning to support vital decisions on the demarcation of areas unsuitable for habitation. So this is really nice feedback that we know that this data has been really put into use in the city for the planning, and yeah, this is a really nice use case, which we think is very important on the ground. And with that, I am already at the end of my presentation.